Thank you. We're going to be talking about probably like two things that you might not have thought went together, AI and NASCAR, right? But bear with me and we'll get through this together. So I guess first question I have for people in the room is, who in the room has ever watched a NASCAR race before? Wow, that's like more than I thought it was going to be. I guess that's probably all the people that are here at the conference that have watched one are here in the room here today. So full disclosure, I grew up in New Jersey from New York City. I had unsurprisingly never watched a NASCAR race before I started working with them, but now I've seen a lot of them and have worked pretty closely with them over the past year. So based out of New York City, like I said, already walked through my work experience. Worldwide technology, I'm guessing most people in the room have probably at least heard of WWT since we're in St. Louis, right? So large, privately held, $11 billion technology solution provider. The group that I work in, Business and Analytics Advisors, is the part of Worldwide that focuses specifically on data, AI, data management, data science. Actually, I have Mike Catalano, one of my colleagues on the team, who's a data scientist who works with us, who is going to jump in and help me out if there's any kind of questions specifically around the modeling and work we did there. So that's a little bit of my background. That picture of me on the top right there is with two other consultants from the team. That was us at the last race of last season, which is at Homestead near Miami. One of the first times we got to test the app in action. Yeah, you can tell we're at the track because we got those headphones on. If you've ever been to a race, you know that you need to have some sort of earplugs or headphones on, otherwise you can't hear anything. So let me see with, I don't know if this is going to work. I have like a little, you know what? I'm just gonna go ahead and forget that. So I had a YouTube video. If you go onto WWT's YouTube channel and just search for Richard Petty Motorsports, there's kind of like a 90-second advertising video that shows some information on the partnership. So I'm going to give a little information about the client and kind of an early non-AI use case we did, so you get a sense of the type of data that they have available, and then we'll get into the computer vision piece. So one of the ways that I try to explain how a NASCAR team works to WWT. I actually use this slide internally at WWT. WWT does a lot of work around technology supply chain. So I'm like, one easy way, if you've never watched a NASCAR race, to think of how a race team operates, it's a supply chain business, right? That's trying to achieve the business outcome of win races, right? That's ultimately what they're trying to do. So every week, pretty much every week from mid-February leading up to the Daytona 500 to mid-November at that Homestead race I mentioned before, every race team, and Richard Petty Motorsports, who we work with, and WWT sponsors, right, that's how we got involved with them, is no exception. They're going through this process. So early part of the week, they're designing and building cars for a race. This is a little bit inaccurate. They're actually usually designing those cars a few weeks in advance. They're not building the car for that same week. But designing those cars at their shop, in this case that's in North Carolina. They have some pretty sophisticated physics and engineering simulators they're running to figure out how they should tweak the car for each race. And different kinds of tracks or conditions or length of track, even what the weather is going to be like, that can affect the way that you configure the vehicle. Then the car, I mean, this is really where the supply chain aspect, you have to physically get the car from North Carolina to wherever the race is, right? And that could be anywhere in the US from up by me in Pocono or Watkins Glen in New York. It could be as far out west as Sonoma in California. They have a race in Southern California that they just had in Fontana a couple weeks ago. So getting the car physically out there. Then Friday and Saturday are typically spent on practice and qualifying runs, right? So they're doing these runs to see how the car behaves on the track, make adjustments in the garage, qualify to figure out what order they start the race in, pass some pretty serious and they would say probably onerous technical inspection before the race to make sure that they're allowed to get out there according to NASCAR regulations. And then they're actually competing in the race, right? The race is typically 3.5 to 4 hours, and a lap around the track can be anywhere from 20 seconds to 1 minute and 20 seconds, depending on the length of the track. They actually just had the race this past weekend at that one that falls on the very short end of the spectrum at Bristol, right? They're zipping around the track in 19 or 20 seconds. And the team is making strategic decisions often after every lap. They're thinking about when to do pit stops and some other things that we'll get into. So, no, don't want to show that. Okay. So for this project, or for our early work with RPM, we really decided to focus on what happens once they reach the track. There's obviously a lot of interesting stuff that could be done from an engineering standpoint around how they're building the cars and doing simulation. That also requires a pretty significant amount of knowledge from an automotive engineering standpoint, which is not in WWT's wheelhouse, at least not yet. So we kind of focused on that area. So what were the challenges that Richard Petty Motorsports was facing? There's a few. So one is during race weekends, they're very dependent on kind of outdated OEM software. OEM in the racing world, usually when they say, because I know that can mean something very different in a technology context. OEM here, their big OEM is Chevy. They're talking about like the manufacturer of the car, so Chevy, Ford, Toyota. Outdated software that was provided by their OEM that slowed down their decision-making process because the interface was difficult to use, or you weren't allowed to have it on a mobile device. It was kind of like a thick client that you were installing on your desktop. The other piece is, if you're familiar with NASCAR, Richard Petty Motorsports is not one of the big teams from a funding standpoint. They just have one car. Their IT department is one guy. So this is like this one guy who's doing everything from maintaining their one rack of servers in the closet at their offices in North Carolina to provisioning me a RPM email address when I needed one when I signed up. This one guy is doing everything. They work with kind of a partner race team to help provide some additional capacity there, but they don't have a software development capability. Data sources, and this is not an RPM specific problem, but data sources each had their own application and data repository, so very siloed information and data. And they also, when you think about this team, and this team is maybe made up of 20 or so people, if you think of the people that go to the race each weekend and some of the engineers that work back in the shop, they don't have experience translating business requirements to software development requirements, for example. They're engineers, right? There's one guy, he's the tire guy. He knows more than any of us will ever know in our lives about anything specifically about tires, right? But they don't necessarily have folks who are sophisticated in talking about those types of requirements. So it's almost like you can think of these challenges as being very much like the challenges like a small business might face, right? Which is really how they're operating. So the initial thing that we built for them was not an AI use case, right? It's data that could be used as the foundation of an AI use case, so I'm not going to spend much time on it, but was a dashboard application that brought together data from these different sources into an AWS environment, because again, they don't have data center infrastructure that they could use to host an application. And this is something they use on a weekly basis at the track, including during the 2019 season. So when you're thinking about data sources, right, these are the big data sources that they have available to them, at least initially. There's one other one that we're going to talk about, which is where the AI use case came in, but there's timing and scoring. So that's literally the official NASCAR feed that says for each driver during the race, how fast was their lap time, what position are they in. If you go onto NASCAR.com and look at the standings during a race that's updated in real time, it's coming from the same feed that these guys are using. It's all one source. There's pit road officiating, which is a NASCAR data source that's only available if you're on the @track network, which is telling you what happens during a pit stop. How long was the pit stop? How many tires did they change? Did it happen during a green flag or a yellow flag lap? And then there's some very basic car telemetry data. You would think, right, so NASCAR, obviously a very engineering-driven sport, and I think a comparison gets made a lot of times to Formula One, right, one of the other really popular racing series. One of the big differences, at least right now, between Formula One and NASCAR is Formula One places very few limits on how much, like, IoT or telemetry data you can capture from a car, right? I would encourage you actually to Google kind of like F1 analytics or F1 data science. They're doing some truly remarkable things, and a lot of that is because they can slap as many sensors as they want on that car and gather that information during the race. NASCAR didn't have telemetry data available to race teams during the race at all until a few years ago. Actually, part of the origin story of it is telemetry data was made available to fans in this app called Race Vision, I think is what it is, when you're at the track, and it tells you a few very simple things, so like where the car is on the track, what's the steering angle, so what angle the steering wheel is, I think throttle, brake, and RPM. I think those are the things that you're capturing. And it was only for the fans. And then one of the teams that had more of an IT department, one of the more enterprising teams said, hey, the fans have access to this sensor data, we don't even have access to that. Can you hack something together for us to scrape information for that application to use? Which they did, and then NASCAR got wind of it, and they're like, okay, if teams are gonna do that, we might as well make this feed available to everybody and also charge them for it, which is part of it as well. But it's still very basic. It's just kind of a few IoT data points. So we took that data, we brought it into this AWS architecture, made it available to them during the race, and they had a timing and scoring application before that showed some of this information, but it had to be viewed on a desktop computer. It didn't bring all these different data sets together. But again, this is mainly around descriptive analytics, right? Something that we're working with the team on this year that we're hoping to be able to do is use information like this to, for example, predict when they should do a pit stop, and also maybe predict when other drivers are going to do a pit stop. That's kind of the initial really important business use case of what you can do with this data, but what you're seeing here is very much descriptive. And this is just kind of a little bit more close-up view of it, and it kind of just points out, multiple data sources. This piece here was the timing and scoring. This is the pit data that we brought in. The ability to view data and some data visualization. A lot of the work was as much around UI and user interface as it was a data standpoint. And this is what it looked like in action, right? Because it just makes me feel, it's like a proud father when I go to the race and I see whenever I see an application, yeah. Any software developers in the room know that it's an exciting moment when they're actually, I think the first race we went to, maybe back in like mid-September when we first gave this to them, I could tell they were kind of only using it because I was there. They're like, oh, Chris is sitting up here, like, yeah, let's click around, and then go back to my old app. But by the time these pictures are from Homestead, the old app was nowhere to be seen, and they were really using this, which was cool to see. So this is actually in the pit box at the track. It become important because I'll talk about the users of this AI use case that we're developing. So these are people that are sitting, they're elevated, right? So they're up maybe, 15 or 20 feet above the ground. You kind of climb up a ladder to this booth. They're kind of overseeing where Bubba Wallace, in this case, the driver for RPM, comes in to do a pit stop and seeing the track, and this is where they have kind of these different visualizations. The people that you see here, this is the crew chief, who's kind of like the main guy who's responsible for race strategy, and then the other guy on the left is one of his supporting engineers. You can see there's still some pretty low-tech stuff here, though. And we see this like whiteboard here. That's what they erase and update during the race to tell them when they should do their next pit stop and what tires they're scheduled to change onto the car at that time. I think replacing that whiteboard with something else would be a good 2019 goal for WWT with these guys. And then this is the same view back in the hauler, right? So back in the garage area, you have people who are not in the pit box looking at these same sort of views. Okay. So these pictures were at the end of the 2019 season. So something we're working on now, AI use case. Where does AI come in for NASCAR? This is an interesting one because I think the use case is like the most classic of artificial intelligence use cases there are. It's like object detection and image classification. So I don't think there's anything mind-blowing here from a data science technique standpoint. But I think what's interesting is just to see how an industry like NASCAR, a NASCAR team is using something like this, how you might not expect it. So during a race, one of the other data sources, it wasn't listed on that page before, that they have access to are these high-resolution photographs that are taken hundreds, if not thousands of times during a race. Actually, it's definitely thousands of all the different cars as they're going around the track. The business use for that, right, is if you're that crew chief, Derek is their crew chief, sitting there, and you want to understand, okay, for our car or a car that we're racing with, how far is the bumper or the splitter above the pavement? Or I think there was maybe a little bit of damage done to our front left tire, but I'm not sure. You want to be able to tell that before bringing them in to do a pit stop. And if you don't have those pictures, really the only way that you can tell is based on what the driver thinks, right? Which if you talk to any crew chief, they'll tell you that is not always accurate, right? What they think. Or hopefully your car is on TV, on Fox or NBC, and you are able to see it going around. Otherwise, these cars are racing around at 200 miles per hour. You can't pick out something that's going on. So they take these high-res photos. So they're very important to them. So the way it works today is photos are taken. They're made available through this feed, I think through the OEM, right? So through Chevy in this case. And then their team puts it onto like a network attached storage that they have at the track, right? So they're just dumping these images on there, unlabeled, completely like randomly generated file names, all dumped in there. Then there's one of the engineers, so you saw that thing I saw, there's the crew chief, there's the lead race engineer, and then there's kind of like a supporting, more junior engineer. And we were watching him during the race. One of the main things that he's doing is opening up basically like a Windows Explorer folder on his laptop and being like, where the hell are the pictures of our car? And just like, okay, yep, all right, found one, open it up, show it to the crew chief, and yeah, you get the idea. And it's something where it's a small enough number of images where it's doable, right? It's not like you're asking this guy to sort through 50 million images and it's an impossible thing to do, but these guys are trying to make decisions maybe every 20 seconds. Like it'd be great if this guy was doing something else besides just sifting through the folder here. So from our standpoint, obviously the first thing we thought of was, well, that is like a great AI use case, right? Like wouldn't it be great if there was a model that could kind of look through these pictures and tell you not just your own car, but label it by what car is in the picture, and just for a minimum, like MVP version of what we're doing here, just sort it in folders or tags by which car is in which one. So if you click 43 car, okay, you see all the pictures of the 43 car. One of the challenges with this is, with training a model like this, and again, if you watch NASCAR, you'll know this, the cars don't look the same from race to race, right? It all depends on who is sponsoring the team for that race. So if a different team is sponsoring the car, it will look completely different, and we'll show you some examples of that. But there are some things that are consistent, which is what made us think this is possible, right? The number and the font of the number of the car, that remains consistent from race to race, for example. Okay. So, I mean, this was, again, what we were trying to do here. These steps will probably be pretty familiar to you if you're familiar at all with kind of this type of AI use case. But it was take these images, object detection, detect where a car is in the image, label those cars. And part of what was interesting about this one is how we figured out a good way to kind of label those cars efficiently. Train a neural network to classify them. When we say classify in this case, it's which car is in which picture. And then the fourth arrow here is something, implementing this operationally is something we're working on as we speak, and I'll explain some of the challenges around that. So they gave us 150,000 images. It's basically all of the images that they captured to date from the 2018 season at this point. So it's probably from like February to maybe August or so when we started working on this. Hardware that we had available in our lab environment at Worldwide, so stored on flash storage. For this one, we use GPU compute for training the models, but definitely not the only way you can go. Some different, standard, well-known machine learning libraries, and some pre-trained image classification neural networks. Right, so this is kind of what we started with. So this, I think, ended up, I mean, Mike can correct me if I'm wrong here, but like this was kind of like the easier part, I would say, right? Like this is a pretty well-defined problem. And the good thing, in terms of detecting where a car is in the picture, the nice thing about these NASCAR pictures, for the most part, is they're the type of images that are really easy for an object detection sort of algorithm to work on, right? They're very often black pavement, very colorful thing on top of the pavement, right? It was not that hard with a pretty high degree of accuracy to tell this is a car versus this is not a car. So it was basically taking a picture like this, identifying where the cars are in that picture, and then separating it out into separate image files, right? So 150,000 image files became more image files because we were taking the individual car in each picture that we were going to use for training purposes. And I guess MobileNet SSD, is that the name of the model, I guess, probably that we use the out-of-the-box sort of model to do that. Cool. So pretty straightforward. Okay. So then we had to label these images. This is like the bane, I think, of every AI or data scientist's existence. It's like, all right, we got this great data set that we want to train a model on, but now we have to label all these images, right, that are completely unlabeled. So we actually kind of developed a multi-step process to do this, so we didn't have to by hand label 150,000 images. And we didn't have the ability to crowdsource across WWT to say, hey, go onto this website and label these images, the way it might work with some other larger businesses. So we actually did an approach, and I'll show a couple slides on this, where we labeled a subset of the images by hand. We trained a model on that subset that we labeled, and then had the results of that model, doing that classification, which it did a pretty good job on, presented those results in a little bit more bulk format to the end user. So basically the ultimate result was, instead of people labeling images one at a time, they were looking at a picture like this one that said, hey, the model thinks that all of these pictures are of the 12 car. Are any of these not the 12 car? Right? So it becomes, instead of one at a time, it becomes a look at 40 or 50 images and just pick out the ones that are not. And then once you do that enough, retrain the model, it gets even better. So it was kind of like this half automated, half manual process that we used for training the images. And I think it's something that we have and we will use, like this kind of methodology, for other use cases where it makes sense, where it's like it's a big enough data set where you don't want to be manually labeling each image, but it's small enough where this type of approach would work. So this is kind of this kind of gives you an idea of the images that we worked with and how it worked. So it started with hand labeling about 7,000 images. So we kind of split it up amongst 4 or 5 people on our team, myself included. So that was like me on a Saturday, watching whatever on TV, 5, 9, 12, 42, right? Kind of going through and labeling those images. But again, split amongst the number of people we had on our team, was not too onerous of a task. We were able to do that in a couple of days. Then, that training the model based on those hand-labeled images allowed us to correctly label another 43,000 of them, but then there were some that did not fit, so we said no for those and kind of reran it. So it's like this interesting. I like this example because it shows you some of the. It's some of the real behind-the-scenes stuff that needs to happen sometimes to get a model like this to work, right? It's not quite as simple always of just automatically having this really nice, great labeled data set to run your model against. So by the time it was all said and done, we kind of went through this process a little bit, enlisted the help of some folks on the team to help us get through it, and then we had this really well labeled data set. And this is just the view again. So this was the view of me on the weekend looking at, enter the number 12, hit submit, and then this was what the web app, obviously very simple looking, but again, now you can just look at this and very easy to pick out, right? Which one of these is not like the other, right? So we were able to do that and kind of submit that and capture that information. This is what the distribution of images looked like, just in case you're interested. So basically each bar on the bottom here is a car, right? The number of the car. So again, if you don't watch NASCAR, all cars are identified by a number. It's the same number from race to race. The 43 car is the car that we sponsored. You can see them on here. The kind of long tail that you see over here, I guess it's not that long. It's the same length as the first half of the image. But the smaller bars here, these are cars that maybe they only participated in one race during the season or one or two races. The ones on the left are the ones that you're seeing every week, week to week. So we were able to get a pretty nice data set together. Okay, so then it came to actually, let's figure out how we're going to label these images. And we started with using pre-trained models. Again, kind of image classification. It's a very well-defined problem. You have all of these models. I think most, if not all of these, were built on the ImageNet data set, right, which probably at least some of you in the room are familiar with, right? Very popular, well-known source data set used for training image-based neural networks. So we actually, I think the ones that we used actually for this, and we'll show you how it worked together, were the ones you see up top. But gives us kind of a head start. We didn't have a massive enough data set that it really would have made sense to start training the model from scratch. You know, we had a lot of images, but in the grand scheme of, you know, compared to something like ImageNet, not the same thing. So we kind of used a combination of models. And,
Chris,
oh yeah.
Is there a reason why you picked those four instead of other combinations?
That's a good question.
Yeah, I think just based on popularity and performance.
Yeah.
Did you use them in Ensemble mode or one at
Yeah, I think Chris will get.
Yes, we did. Okay. Yeah. So, and again, ImageNet. Again, I think for this audience, I don't need to tell you this, but just in case, you know what ImageNet is, right? It's this data set that was used for training those images. So it's a great way, models that are trained using ImageNet, it's a great way to get like a head start, basically, or a jump start on any sort of image classification model. Unfortunately, they don't have a specific NASCAR car subset for the models would have worked even better if that was the case. So, and this kind of just shows you how the classification model worked at a high level, right? So we did take the cropped image and compressed it, made it a lot smaller, because we kind of realized that the performance that we had worked on much smaller images, which helped in terms of the training time. I don't know if, Mike, if there's anything else you want to say about, basically when we get to these types of slides, I'm just going to look at you and say if there's anything else that you want to add to this, but I think pretty straightforward. The ensemble piece is the interesting one, right? So the training time in the environment that we had, training that data set in the environment that we had in the lab, again, GPU compute and the flash storage, it took, yeah, it says less than 2 hours, but like we should have said, 76 minutes. That's a lot less than 2 hours. So, an hour and 15 minutes to kind of train it across these different models. We basically took the 4 models that you said before and trained it on color versions of the images, but then also grayscale versions of the images as well. The thinking was doing these images in grayscale could eliminate some of the noise of the different sponsor logos and help the model kind of hone in on the specific the numbers and the distinguishing characteristics that are the same from race to race. So the question came up around ensemble, right? So this idea of taking the results across these multiple models and bringing them together. And I think I'll speak for our data science team. I think in general, not just with a problem like this, we've often had a lot of success using an ensemble approach to solving data science problems. It was absolutely the case here. So this shows you kind of, so first of all, when we trained it, we basically trained it on a set of races, the first 11 races of the season, and then we validated or tested it on the next 3 races, right, to see how accurate the model was. So this is basically the accuracy results using images from races 1 through 11 for the training on the images from races 12 through 14. And you can see, like, using it across these different images, the results are pretty good, right? they're all hovering around the low 70% range. It's probably at a level where the team wouldn't be like too mad at us if we classified it in this way, but would also be like, hey, there's a quarter of these images that are not labeled correctly. It's like not quite the performance level that we were looking for. So what we discovered, right, is, this is kind of a different version of this chart that's saying if this many of the models agree on which car is in the image, you can see the accuracy spikes, right? So if you have 3 of the models that agree, but once you get up to 5, 6, 7 of the models agreeing, yes, this is the car, the accuracy level for the predictions went up to the range that we were looking for, right? So the ensemble approach really was the way to go. And I think, to kind of get us up to that higher percentage range. Now, obviously, there's going to be a lot of images that are not going to have models along this right-hand side, that many that agree. It'll be more in the 3 or 4 range, but it at least allows us to get closer to where we wanted to get to. And the idea is, as we kind of continue working with them and bringing in a larger and larger data set, it allows us to bump these accuracy numbers up even higher. So I'm just seeing how, cool, okay. So really what we learned from that part of it, and then I'll talk about like what we're thinking about now, which is kind of taking this model and how do we operationalize it, which NASCAR, there's some very interesting limitations that they have for running a model like this, which I'll explain. So the main insights. So the first one, labeling, even using that, labeling is time consuming, right? Again, probably not like a novel thing for the people in this room, but continuing to explore methods that allow us to more quickly label information in bulk. That bulk verification was a big breakthrough for us in terms of being able to reach a result more quickly and being able to spend more time testing and honing the model and less time on labeling. Using pre-trained models when possible, which again allowed us to accelerate our timeline, and then using ensemble predictions to improve accuracy. I mean, I think the important thing here is the first 2 items especially. They're very, we're talking about it in the context of this NASCAR use case, but it's all about like speed to value, basically, and things like that can help kind of accelerate that process. No pun intended. I've actually discovered that like when I've given talks on this or talked about this with people, it's like people use a lot of like racing metaphors in their life. So I always end up saying something like hit the ground running or accelerate or, anyway, so I apologize. Kick it into high gear or whatever. But it kind of all has to do with time to value. And again, this is, before I get to the last piece, this is just kind of what this looks like in practice, right? The 42 car, there it is. The worldwide technology car, the 43. Colors seem kind of weird on that one. I don't know. Do we actually have a car that color at one point? It's very strange. Detecting multiple cars in the image, right? So kind of what this looks like in terms of the model classifying it. So the last piece here is around, productionalizing this. So part of the challenge with this is it's like an infrastructure challenge, right? So these images are only available via the @track network, right? So if I'm at home, right, and I want to access this data, and again, I have the right credentials from the race team, it's like the pit stop data. I basically need to VPN tunnel into the @track network and then access the data that way. If you've ever been to a NASCAR race, maybe this won't be surprising because the Wi-Fi usually is not very good at those races. Network bandwidth in general, whether it's for teams or for fans at a track, is an issue. I'm gonna forget now what exactly the number is, but basically the NASCAR teams, they are paying for kind of their internet access at the track. They're paying like $1,200 a month for internet speed that's slower than your cable modem at home. I mean, it's like really criminal almost, how it works. So So as a result, they're very sensitive about bandwidth that's being used by different applications at the track, right? And we originally talked to them like, okay, great. We'll set something up here. We'll kind of, as the images get downloaded, we'll shoot them. So this was built in AWS as well, or it was built, yeah, I believe it was built using AWS, or at least the idea was we were going to port it into AWS. We'll take the images, we'll shoot them up to the cloud, we'll run the model against it, we'll send the classified ones back down, and they can be used by whatever application. Which is originally when we kind of put this picture together, and their answer was like, that's probably not going to work, right? Because if they're thinking about the bandwidth that it will take to be uploading and downloading these images at the track, they're like, the team is not going to allow us to do that because it's not going to allow them to run all the different applications that they're running. So one of the things that we're exploring doing right now, it's an effort that we're hoping to kick off with them in the next couple months here, at least figuring out how to do it, is to try to figure out a way to have a local high-performance compute of some kind, whether it's GPU or FPGA or whatever makes sense, to actually run the inference against the different images locally at the track instead of shooting it back up to the cloud and doing it that way. And that's kind of where some of WWT's expertise comes in. If you know WWT at all, there's a lot of experience in kind of the hardware and infrastructure space. So when I started to mention this problem to them, they got excited and they're like, okay, we can figure out some ways to do this. It's not something we're doing yet. I think the other piece that we're trying to do is, it's a new season. All of the car designs have changed, right? Or a lot of them have changed, right? New sponsors. So we're already, you can train the model up using those images, but we're like, what's a way that maybe in a quicker, more systematic fashion as new car designs are introduced, that you can kind of update your model for kind of its ability to classify images. And the main time that they're using these images is during a race, right? They have practice and qualifying that I mentioned before, but practice and qualifying, it's not as important for, the car is coming back anyway. It runs a couple laps and then it comes back. One of the ideas that we have and something we're exploring right now is doing training during practice and qualifying, kind of some supplemental training of the model as we kind of get new images for the first time of cars that have this new design, and kind of retraining the model and then kind of pushing an updated version of the model at that point that's kind of taking into account what it's seeing during practice and qualifying a little bit. That's still very early days. That's more hypothetical than something that we have in practice, but it's kind of another one of the big problems here where you're not just trying to tell, is this a car? You're trying to tell, okay, is this the 43 car? And for some of these teams, like the 43 team that maybe are not as well funded, sponsorship is changing often, right? So that car design is changing. The 43 number is the same, but the design is changing. So figuring out ways to do that is a big focus as well. Then obviously we would love to take these results and integrate them into that dashboard application I showed you before, right? When we talked to them about, hey, wouldn't it be great if in this one dashboard you have the timing and scoring, the pit stops, the sensor data, and then if you click on the 43 car, all of the pictures from the last 10 laps pop up in a little view there, and they're like, yeah, that would be amazing, right? So kind of once we kind of figure out how to operationalize this, putting that into this existing data platform and application we're building for them will be the next step. So before just kind of opening it up to questions for a few minutes, the one other thing I'll mention is this was obviously the very abbreviated version of talking about the work we did for them. I put a link down here. Even if you just Google WWT AI development, I'm pretty sure this is the first link that will come up. We have now, I think, 6 or 7 white papers on the site, one of them about this work. What's cool about them is they're white papers on an AI development topic. They're all authored by some combination of our data science and engineering team, but they're all in service of a customer problem we were trying to solve. We have an R&D function at Worldwide, but as great as our executive team is, they're not willing to sign up for us just doing R&D all the time and get back to us in 6 months. So when we can show how it ties to a specific customer opportunity, it's a lot easier for us to get the time and funding to do it. So what's good about it and why we wanted to start sharing this in the form of these white papers with the larger community is they're less theoretical sort of white papers around AI. They get into more of the practicality and a lot more of the detail about how this process of using, labeling the images and the object detection and image classification and the ensemble approach. There's a lot more detail on there. So if you go to this link, I think it's you scroll down to the bottom and there's like 6 or 7 of them. If you click on it and sign up for an account on the site, you can kind of download the full white paper and read about it in a little more detail. Yeah, so that was the presentation. I think we have like at least a few minutes, right? Yeah, 10 or 15 for questions. So yeah, any questions?
I might have missed the first part of it. So why are they looking at the images again?
Oh yeah, just repeat that. Yeah, why are we doing any of this? Why are we here? So yeah, so the why is these images are valuable. The short version is these images are valuable to them because it's telling them what's going on with their car and other cars during a race when normally they can't see it. So there's these high-res images that are taken of cars for the purposes of the teams being able to see what's going on with their car during the race. Otherwise, the only time they could tell in terms of like looking, is there damage to the car? How far is the bumper above the pavement? The only way they could tell normally that is if their car is on TV, happens to be on the NBC broadcast, or they go in for a pit stop, and obviously they can get a really good look at it. So what we noticed during the race is there was a person on their team who was spending a lot of time manually sifting through a Windows Explorer folder full of unlabeled images to say, like, where the hell are the images of our car? So we're like, wouldn't it be great if there was a way to automate that process? So that was kind of the business need.
The second question I had is, you said that the data was not fairly balanced, like the 64 car numbers, the number of races were less. So did you use any techniques to kind of balance the data set or augmentation or anything of that kind?
So actually, we took,
You have to press the button there.
I give it turns green. Yeah.
so we took, if you look at this tail here, we actually just grouped these into basically another class. But we found that we had sufficient samples for all of those other car numbers there. So at least 1,000 images per car was enough to get pretty decent results.
Yeah. But yeah, that was a good clarification that I neglected to make there. Yeah, the model was not able to successfully detect. It was we basically said we could detect that it's not one of the cars that we have more than 1,000 images for, but otherwise we just lumped it together.
I would love to know, is your next sales opportunity trying to actually determine splitter height and 3D model of the car after you've collected all these images to try to give them that more real-time data?
Yeah, I mean, and it's funny, someone mentioned during the keynote, kind of, and it reminded me of this a little bit, like looking at an image of a car to tell how desirable that car would be to a consumer, right? But it's kind of getting at, so the short answer is like, yes, we would love to explore that, which is, the logical next step is, okay, you can tell which car is which. The next piece is, okay, what are they actually looking for in these images, right? And typically, mainly what they're looking for is damage, or something like you're saying, splitter height. That's often what they're looking at, right? They're looking at, because they want to get, it's a proxy for like how much the tires have worn down, seeing how high that splitter is above the pavement. And you're right now when they're looking at it, you see them doing it. They're like taking the image, they're like zooming in, and they're like, okay, like it looks like it's touching the pavement, maybe not. And so yes, that would be like, especially starting with doing it focused on their car, on the 43 car, which they have good knowledge from an engineering standpoint of what it's supposed to look like, and then expanding it from there. So yeah, absolutely.
So I have a question regarding the image cleaning or image pre-processing part. I'm sure it's like 150K images. So what steps did you guys take?
So that mobile net model that Chris mentioned, it's a single shot detection model. We actually just use that pretty much right out of the box. So we feed all of these images in. We have the model tell us where the cars are in the image. And then I think just as an added insurance policy, we said, okay, only return those that were 99% greater confidence. So we take all of those. We use that information to crop the large high-res image, and then downsize each one of those so that it's more appropriately sized to be fed into training a classification model. So it worked pretty well right out of the box.
And my second question is, conceptually, 28 categories are too much, conceptually, because if you want to categorize into 28 different categories, it's too much. So did you face that need, to regroup again into multiple chunks, or it was fine with 28 big categories to classify?
Yeah, so I think it's definitely not a trivial problem. You'll notice I think our accuracy was 81%, which is good. It's not outstanding, but I'm not sure if we should. Certainly, the fewer classes you have, the higher your accuracy is going to be. But 81% we were satisfied with that, I'd say.
Yeah, I think from a business standpoint for them, I'm not sure if we actually did this or not, but even one logical place for us to start would have been, so the 43 car is the one that they're most concerned with, right? So at a minimum, being able to say 43 car, yes or no, right? And almost grouping everything into an other category. We didn't do that here, but it could have been a logical way to start, right? If we felt like it was too many categories to run the model against.
Was your ensemble, a linear regression, just coefficients weighted? And did you consider a random forest or other ways to ensemble the results?
I think it was just arithmetic mean of the softmax vector, right? Yep. Just a simple mean, yeah.
Thanks.
Great. Well, if that's all the questions we have for today, thank you all. Thank you very much. This is really fascinating.